Yeah, so thank you everyone for being here. I mean, this is kind of weird. It's weird for me to be sitting in my room doing a keynote and not on a nice stage in a hotel in Chicago. I really appreciate all of you being here. I mean, at these times, I know that sometimes it's hard for me to motivate myself to, through everything that's going on, to continue doing my day work. So being here, learning something new while the world is in a very unclear situation is really awesome. And you should give yourself a huge high five just for being here this morning. So in this talk, we're going to talk about kind of how microservices evolved. So we've been, like, the collective we, the worldwide we, have been doing microservices for more or less 8 years now. So it seems like a good time to kind of stop and review, what did we learn? What were microservices like when we started? What were the problems? How did we solve them? What is the state of the art of microservices today? And what I really hope to see in the future. And at Confluent, we use a lot of microservices to run our cloud. So I'm going to speak a bit toward our experience, and also a lot of our customers using Kafka and Confluent Cloud to run microservices. So I'll also share some things that I learned from the way our customers do things. So with that, let's go all the way back to the beginning. We used to have monoliths, right? We used to have this one big app that ran the website and talked to the database, and talked to the other database, and did everything, had all the business logic, and it was just one gigantic app. And at some point, we figured out that it's complex, it's difficult to maintain. If you have to do a release, it takes forever because you have to coordinate gazillion different teams. Every change has to be tightly controlled. We suspected it's slowing us down a lot, and we suspected that there is a better way of doing things. And the better way we suspected is to take this big monolith and break it down into those self-contained units called microservices. These units had their own context of execution, they had their own public APIs, they were represented something that the business wants to do. And a team owned one or more of them, and the idea was that you own those microservices, you can evolve them independently, you can move faster. And to a pretty good extent, it worked. We had those things and we could move faster, we could deploy independently, we could be much more agile on our execution. But you can't completely, like, no service is an island. You can't completely get away from the fact that it used to be a monolith and we broke it into pieces. So what we really have is those microservices that need to talk to each other, right? I mean, you can't do everything your own. You have to send requests and get responses from other microservices. Most of us do it using REST APIs. So you have a REST endpoint. Normally you send JSON and you say, okay, I have an order. Can you please validate it? Oh, thank you. It's a valid order. Fantastic. Do I have enough stuff in the inventory? Yes, I do. Fantastic. And this thing, again, to a great extent, worked well for a while. But we started discovering problems with that model. So the really basic thing of doing synchronous request-response communication basically led us to pretty tight coupling between services in some ways that I'll explore in a second. And this tight coupling almost brought us all the way back to where we were. So that's the things that people call distributed monoliths at times. You have microservices, but you have all the problems of monolith, of having to coordinate all the teams, of doing those big bang releases, and a lot of the fragilities that comes along. So let's dive a bit deeper into some of those problems. The first one is that some of us made a mistake of exposing too many of the microservices directly to customers, which basically leads to a point where evolving them becomes really hard. The other problem is that you kind of you have to be a pretty good architect to architect microservices environments, and very few people got it right the first time. And one of the things that happens is the question of who's responsible for what, right? The whole point of microservices was that each microservice is only responsible for itself. But if you send a response to another service and it doesn't respond, what now, right? So you kind of have to somehow take responsibility for at least the other service not being available and being able to still do something intelligent. And there is a lot of redundancy. Every team basically ends up solving a lot of those common problems on their own. And again, we kind of evolved into shared infrastructure, but then shared infrastructure sometimes bring back the monolith problems. So we have some issues around who is responsible for what and which functionality goes where. The other thing is that we haven't completely de-risked our changes. If I'm the inventory service, and a lot of people are looking for inventory, I don't really know who they are, and I don't exactly know what part of the functionalities they depend on. So making changes, even with good APIs and good contracts, which are tricky in themselves, is not as simple as it sounds, and you still need to do a lot of validation around that. And then the other thing is that I suppose that we want to move independently, and suppose that I'm a brilliant engineer and I have a great idea for a new shared service. I can't independently put it out there. I need to go around and convince everyone to use my service. And that's it can get a bit political. And it also has this bad circular effect where I can't really prove that what I did is valuable because nobody is using it. And I can't really convince anyone to use it because I can't prove that it's valuable. Like I need to ask you for a share of your time in order to basically prove that my service is valuable, but you're a busy person. Everyone here is busy. So just getting your time to experiment with my service becomes really hard. So we're not quite as independent as we'd like to think, and we can't quite move fast as small units as we'd like to think. And then the last thing is that I think we discovered over time that using HTTP and JSON as a means of communication, especially when it becomes a high bandwidth communication, is actually pretty slow and very compute intensive. I think there is a website of how much carbon people are using because they're using JSON and not a more efficient way of serialization. And it's kind of a joke, but you know, JSON may be killing our planet. So we should be a bit mindful about what we're using and how we're using and the overhead of our communication. And we're going to talk about all these problems and how we solve them. Like all of these problems are to an extent solved by now. So we're going to look at, except politics. Politics is not really ever solved. We're going to basically look at that. We have all those problems. We really could be doing a lot better. And I would just want to share some patterns that enabled us to do a lot better. So very nice virtually meeting you. Let's virtually shake hands. I'm Gwen Shapira. I've been basically moving data between services and databases for about 20 years in different capacities. Right now, I'm an engineering manager at Confluent. My team is adapting Kafka to run on the cloud, which involves basically making Kafka more cloud native than it was before, which is quite fun. I worked a lot, back when I was doing engineering and not managing, I worked a lot on Apache Kafka. I wrote a book or two, and I'm still tweeting quite a lot about our experiences if you follow me on Twitter. If you follow me on Twitter, you also have a sneak peek toward this presentation. So let's start with the first super useful pattern. It's the first because as a user of any service in the world, that will be literally the first thing you'll run into. So remember we talked about clients that know too much, that you have a client that actually is aware that you have a return service and you have an inventory service and you have order service, and like your maybe JavaScript is aware of it, maybe your mobile app is aware of all of it. And this is too much because it basically makes changes almost impossible. Remember the first rule of clients are impossible to change. You have, especially on mobile clients, you have to go through app stores. And people don't really upgrade. Everyone hates upgrading. You never know when they'll upgrade, so you have to support the old version forever. So it's really having clients that have deep awareness of your APIs and infrastructure makes any changes, any hope of agility really, really not as good as we'd like. Let's put it that way. Where we got microservices, maybe we didn't get the benefits. So to make things even worse, it also means if the clients talk to everyone, it means that everyone is responsible for handling communication with the client, especially authentication, encryption, all those things. everyone is suddenly responsible for that. Means that my app has to worry about things that really it shouldn't have to worry about. And it's a lot of, again, redundant code and redundant work being done in our organization. And I actually am interviewing people now, and the number of people that who worked on solving exactly this problem is quite high. And the solution is quite canonical. You put an API gateway in front of it. And basically clients only know about the API gateway. They don't need to know about everything else. They don't need to know about IPs or DNS names or even the internal APIs. So you get more freedom to evolve the internal APIs as long as the API gateway is consistent. Authentication is done in one place. It's also much more performance friendly because you authenticate once and then you have those little tokens that are much more efficient. So this is a really, really nice pattern. By now it is super, super popular. I don't think I know a single service that doesn't have an API gateway of sorts. And you get really good things. So you get authentication. I talked a bit about that. You get routing. I talked about that. Like the clients doesn't know, they need to know who are the services, where they sit, what their DNS names, etc. You also get rate limiting. And you get it sometimes, if you use the right API gateway, you get it per endpoint, which is really good. Like some operations shouldn't be done all that often. And you don't really, and you want to be able to say, okay, if someone tried to create an account, they should not be able to create another account in the next, I don't know, day, hour, etc. If someone tried to post comment on a blog, probably prevent them from doing another one for a minute or two just to make sure they're not spamming, etc. Super useful. And then logging and analytics, especially audit logs, like who is accessing, what are they accessing, which endpoint is most popular. You have this central point where you can get a lot of information. Super, super awesome. There is a risk in having something that is too awesome inside your organization. The risk is that everyone wants to use it. It's so convenient. It gives you very stable APIs. It gives you routing. It gives you rate limiting. The risk is that every single microservices want to talk via the API gateway, even to each other. And that's a problem because suddenly this is the big bottleneck. And also the people who run the API gateway now get a lot of internal requests for APIs. So they become this one big engineering dependency. All of it is not what we were trying to do when we broke ourselves up into microservices. Suddenly the API gateway is at risk of becoming the new monolith. We don't want that. But it's worthwhile thinking, where did the need come from? And the fact that there is a real need there meant that we had to come up with a real solution. And if you ever heard the term service mesh and ask yourself, why do they exist and why would I want one? Because I think it's been around for 2-3 years, but I think a lot of people are still kind of on the fence whether they need a service mesh or not. So we're going to talk a bit about what service mesh is and why. And it's basically, service mesh is your distributed internal API gateway. So if you look at API gateway, it does what we call north-south traffic. This is traffic that comes from outside your business, from outside your data center usually, but sometimes just from outside your maybe Kubernetes cluster. And it goes through the API gateway and it kind of goes deep, if you think from top down, into your microservices. And then the responses trickle back up. So we want to take this really useful north-south traffic and apply it to what we call east-west traffic. East-west traffic is all the traffic between the microservices in this organization. And first of all, you can see that there is a lot more of them and that it's a lot more distributed. Like it is a mesh. Everyone talks to everyone else. It's very difficult to control who talks to what. And you don't really want everything to go through this settler bottleneck for reasons that I just mentioned. So we need a way to allow those good patterns of handling routing and rate limiting and logging and all those centralized functions in a distributed fashion. And the way we did that is with what we now call sidecars. So sidecar is basically what you'd think of as a component of the application that is not deployed as a separate service, but as a separate maybe container next to the main containers that does every single microservice. The fact that it's in a separate container means that you get isolation and encapsulation. And think about it as a library that grown its own environment, I would say. So the idea is that you can deploy this sidecar next to every microservice. And unlike a library, it's because it's its own service, it's language agnostic. So I can write a sidecar in Go and deploy it next to the Java applications, the Rust applications, the old legacy PHP applications. All of them can get the same sidecar, which really reduces the overhead of the company trying to maintain microservices in many languages, which is really nice. And now you have this shared functionality that is just replicated across the organization. And the way sidecars normally work, especially in a server, like you have sidecar for a lot of things. We have sidecars for collecting logs, sidecars for monitoring. But if you look at sidecars in terms of a service mesh, the way they work is that they're basically a small proxy or a small gateway attached to every one of the services. And when the service talks, it actually thinks that it's talking to itself. So my service is talking to port 7072 on localhost. And port 7072 in localhost is routed via the proxy. And the proxy has enough intelligence to know where to route those endpoints to. Oh, I'm talking to dash orders, it has to go there. I'm talking to dash inventory, it has to go over there. So this proxy is responsible for service discovery. It's responsible for the routing. It can do rate limiting. It can do logging, who is talking to who. It's really, really one of the more useful things that got added to our architectures over the last few years. So we are pretty big fans. I want to show you two examples, like more specific examples of how those sidecar proxies really became the useful things that allow you to get all the benefits of API Gateway without this centralized control point. So one way is service discovery. So, you know, sometimes services change IPs, or even sometimes we change DNS names for various reasons. And this can become an issue, especially DNS refresh times are not really what we want them to be. So we actually want a way to very quickly let services know that IPs have changed. So the idea is that proxies do service discovery, usually by talking to a centralized layer, like a control plane. Istio is a fairly popular one. And those have service discovery databases, Console, etcd, one of those. And they basically, it's like a mini DNS just for my application. So it asks, hey, I need to talk to / orders service. Who is the order? Where is the order service today? And I get the IP and I talk to it, and my app doesn't have to know. All along, my app is only talking to localhost. So I can really quickly deploy those changes of location across really huge microservices fleet without anyone actually touching their app in any way. So that's very useful, but we had that for a while. I mean, DNSs are not exactly the great new thing. A better example is rate limiting. Remember that some applications don't have the best retry logic in the world. Some of them are, oh, I got a failure, let me retry over and over every millisecond forever. And if you have a lot of them, you can actually like have what we call a thundering herd problem. Like one of the microservices have a tiny small blip in its performance, but now everyone is retrying every millisecond forever. So it's kind of like, the small problem just gets worse and worse, and the poor microservice can never recover because it's drowning in traffic. But if we have those proxies everywhere controlled by a centralized control plane, we can actually either way ahead of time because we were smart, or during the incident, if we discover the problem a bit late, basically say, hey, you know, only rate limit, only allow a retry once every second. And this will allow the service that had a tiny blip of issue to recover without drowning. And the clients may never know that 99% of the retries got silently dropped by a proxy. So this too is super useful way to save your services. Because one of the things about services is that you never know how many clients will need to call you. And we'll talk about that in a moment. Like there could be a lot of auto-scale mechanisms. So you really want some way to control those retries. Clients, like the person who wrote the client doesn't know that there are 50,000 copies of itself. And if my copy retries every millisecond, you'll have 50,000 retries every millisecond. Another pattern that I want to talk about, that's actually a collection of patterns. Like when we talk about, people ask me, what is event-driven programming, event-driven architectures? We're basically looking at a fairly large collection of patterns. I'm going to kind of give you a whirlwind tour because I believe that this is one of the most important things to master as someone who is designing microservices architectures. So I'm going to kind of give you some taste of how useful this can be. So remember we talked about making changes is really, really risky because you really don't always know who is calling you and what they expect. And we also talked about how difficult it can be to add new services because you kind of need to convince people to use your service, and it's really hard because if nobody using you, how can you convince other people that it's useful? And we're looking for a pattern to reverse this problem, basically. So we took the whole request response architecture and we flipped it inside out, upside down, on its head. If we look at request-driven architectures, there's basically two types of communication. I, as an app, either tell another microservice to do something. I'm sending a command, hey, go validate this order. Hey, you tell me if there is enough in the inventory. Or questions. So again, you tell me if it's enough in the inventory. It's a question, like how many of item I do we have left, kind of thing. So either you get information by asking very specific questions and getting very specific responses, or you're telling other services what they should do. And hopefully you structured everything correctly, so what they should do is clearly in their domain and what you do is clearly in your domain. Not always the case. We've seen a lot of cases where you actually leak too much information to the other app because sometimes, like, you know, you're busy, they say, oh, we can do your job for you if you just give us a bit more information in the request. We've seen a lot of leakage of responsibility happens that way. We flipped it on its head and we said, what if it's event-driven? What if every service doesn't really, only communicates by telling other services things that it knows about the world? So those are events. Oh, I heard that we just got an order for I. Oh, I heard that I'm the inventory service and we now only have 10 of item Z left. Everyone keeps always broadcasting important facts about their slice of the world. They don't tell others what to do. Others are independent microservices. They can make their own decisions. And you don't really need to ask questions because you can listen to facts and gather the knowledge that is relevant for you, so you no longer have to ask questions. And this is incredibly powerful. And I'm going to walk you through an example showing how powerful it is. Like, it's one of those simple concepts that is so simple and then kind of opens a whole new world of architectures to you. So the first thing that you have to remember, like as one of the takeaways about event-driven, is that events are facts, things about the world, and they can act as triggers. Like, oh, when I see this fact, I have to do something about it. So it's a way of replicating information and a way of triggering action. And let's make it a bit more concrete and we'll walk through an example. So let's say that I have a small web service running a small shop online, maybe named after a river in South America. And let's say that I'm servicing a request to buy an iPad. So naively, I have a web server. It gets an order to buy an iPad. It talks to the order service. It says, hey, I need to buy an iPad. The iPad says, fantastic, please, I have an iPad. The order service says, fantastic, I validated, I checked the inventory, we have an iPad. It talks to the shipping service. It says, hey, can you ship an iPad to this customer? The shipping service says, fantastic, but who is this customer? Talks to the customer service sends back information about the customer. We pull out the address and we ship. So far, so normal. Like, I think pretty much everyone in this conference can probably hack this in about 60 minutes during a job interview. But if we dig a bit deeper, if we dig beyond the job interview, we have some issues, right? Like, what if the shipping service is down? Does it mean that the order service has to continuously retry to ship? Does it mean that the order gets dropped? Does it get persisted somewhere and then someone else picks it up? It's very unclear what would be the flow and like how much is the order service responsible for the shipping service being available. So what if instead of this request response panel, we used events? And in this example, we're using events as a trigger, as a way to notify and cause actions to follow. So let's say that we submitted an order, and instead of the order service calling the shipping service, it just wrote this big fact that, hey, I got a new order to a huge log of events. So everyone in the organization that cares to know about new orders, from the shipping service to the inventory service to, let's say, analytics, they all know that this thing happened. And the shipping service reads the event and says, oh, I have a new order, I guess, and it looks validated. I guess I have to ship it. And the nice thing is that if the shipping service is down right now, no worries, it will come back in 30 minutes, it will get the event, and it will do it in 30 minutes. And customers, especially when it comes to shipping, they don't really care if it takes you 30 minutes to extra to ship the order. I mean, it's next day delivery at best anyway, so that's fine. So you basically can kind of hide unavailability from pretty much everyone in a really nice way. And you also get a nice log of all the orders that happened over time. You can do really a lot of cool analytics. How long did it take each order to ship, etc. Now the shipping service still need to talk to the customer service and get the address. Is there a way we can work around that? And at this point, we need to know that events are also shared facts about the world. So imagine that the customer goes to the website and says, hey, I moved from San Jose, California to, let's say, Boulder, Colorado. And the customer service says, oh, customer has moved. This is an important new fact about the world. I will write it to our shared log of facts about the world where everyone can subscribe to it. And the shipping service will definitely subscribe to change of address, because shipping service only cares about two things: orders and where to send them. So it definitely will listen to those change of address, and it can basically create its own very small database or cache of every single customer and where they live. It doesn't even take that much space. You get this small mini local database that gives you this information and gets constant. It doesn't get out of that, it gets constantly refreshed with a new facts from customer service being published to this shared log. So you have this small local database with all the addresses. Shipping service is now actually independent, the way we always wanted microservices to be. It can check its local database. Hey, where does this customer live? Fantastic, let me send it over. And this is really huge for the shipping service, kind of owning everything, its entire context of execution, everything it needs to operate. So you can see how event-driven basically gives us a lot more independence. It gives us independence from other services failures, and it gives us independence from other services being kind of a remote database for us. So it gets us one step closer to our microservices ideal. Now, this is if you haven't noticed, that's a subject I'm super passionate about. So I spent basically 3 years of my life just going around talking to customers and users and people like you at conferences about those patterns. And especially if you talk at more old school conferences, like let's say Oracle Open World, people are horrified. Like, how in the world can we have a database, like a separate database for each microservice? Well, first of all, if you're running on Oracle, you probably shouldn't. I'm not going to take any responsibility for your budget. But I mean, they're very small, lightweight. It doesn't even have to be a full-blown database. It can be something like RocksDB, like a local key value store. It can be maybe a cloud key value store. We don't really have, it doesn't have to be a full-blown database for each microservice. But people also worry about things like divergence. Like, what if things go out of sync? Well, it's safe, right? We're all reading from the same stream of events, but you can really have your own version of that. You can, it reduces dependencies. You have much lower latency. Really good reasons to think about it. Okay, so the other thing to remember, the second big takeaway is that if you look at event-driven microservices, they are stateful. They own their own state. And because we're maybe slightly short on time, they also allow you to add new microservices and show their value faster. Because if you have like a great new pricing service, you can just plug it in to read from the same shared source of event and maybe publish prices, and then you can kind of have shadow prices that you can compare. It really allows you to evolve the microsystem by adding more and more microservices on top of the shared log. So you don't really have to convince other people to do something. You can just get the data you need. You don't have to wait for them to call you, which solves a lot of the interdependence politics problem. Now, the other thing to keep in mind is schemas. When we move from request response world to event-driven world, we basically move to a world where it's not really APIs, it's now events. And the medium is not the message. Like, just because we change the way that we are communicating and we start communicating via a log of events, doesn't mean that anything changed about the content that we're communicating. So we have those messages, and they have this kind of nice layout. You're probably familiar with those. But remember that we're also trying to kind of solve the problems that JSON may not be the most effective thing in the world, and that JSON really has very little validation. Like, if someone removes a field, it's very easy not to notice until it's too late and an event was written that will break things forever. And it happens a lot of time. Like, you have this JSON and it has user ID and it has a timestamp, and everyone kind of assumes that the timestamp is of time long. And then someone smart decides to change it to a string, and everything down the line immediately breaks, but it will not break until the data was already written in the wrong format, which is a huge problem. You really need, like, those schemas of the events are really your new APIs, and you need to be very, very careful validating them and making sure that when you make a change, everyone is aware immediately. You don't want to wait until someone pulls the wrong dependency or someone just deploys the wrong thing in order to break your entire system. It's really, really hard to recover from that. At the Kafka ecosystem, we have schema registries where people kind of register all their schemas. Confluent schema registry now supports schemas in Avro, JSON, and protobuf, so you can really pick your poison. With microservices, protobufs are quite nice because they have good support in all those languages, and they are way more efficient than most JSON implementations, maybe not all of them. So you register all your schemas, and if you have all the schemas in one place, you can basically, every change can be validated. Is it still, go to the schema database and run a check. Is it still compatible? And maybe do it via a Maven plugin. Is my schema still compatible? So you can really check those compatibility along the entire line. Now, the latest and coolest thing in the world of microservices is serverless. Basically, we got tired of having to take responsibility for machines. We wanted just our logic. We didn't even want containers. Containers can also be a pain. So imagine just running your logic, your microservices logic as a function. You get an event, magically runs, sends a response. And the nice thing is that if you don't get an event, it magically doesn't run, which means you don't pay for it. These days, when we're looking at a recession, serverless is actually more attractive than ever. And if you happen to be one of those businesses that have a surge in demand because everyone is trying to check your inventory in the warehouse, do you have toilet paper today? You can actually scale it. The serverless platforms will allow you to scale automatically, so you don't even have to worry about that. Really, really fantastic stuff. And also quite familiar, because basically you get events and you respond to them is what our event-driven microservices did all along. Only one thing is missing. We're missing our state, which I just talked about how useful it is to have your local state. Those serverless functions are ephemeral. They come and go. They don't have their own local database. What do we do? Well, we fix things, right? So we really, really want state for a lot of really good reasons. And the way we do it now is to store it in a cloud database. DynamoDB, one of those things. It's not ideal. It can get really expensive. We can do some optimizations to make it slightly less expensive, store some state, Microservices don't get, those serverless functions don't get thrown away immediately, so you can store some state for nearby functions. Not really awesome, but better than nothing. We really, really want our old behavior back. We want this shared stream of events. We want to be able to get notifications for our state and really to control our own destiny once again. So we're kind of looking at this kind of architecture where we have a local database that will keep getting updated by other services, by a shared database, by all kinds of direction, and we can really update each other's states. And this is basically what we see as the future. Microsoft has a bit of it. They call it durable functions. Definitely worth checking out. We think that having serverless with state is kind of where all our efforts came into. We are still looking for a way to really trigger those updates with events. Getting events that just update the state, don't necessarily get a response, and really getting those unified view of having a shared logs that everyone gets updates from. So yeah, I think I finished right on time to the weird tour of where did we start, all the problems we solved, and problems we're looking to solve soon.